All right, 3.6, rate of change. That's actually just slope, you guys. It's different words. If I haven't said this before, math people, we tend to look smarter than we are just because we change words a lot, right? Like once you start saying, I know what slope is, then we say, well, what do you know what rate of change is? And you're like, I don't know what that is. Well, it's the same thing, okay? So I don't know why math people were kind of like jerks like that, but they did. Stinking jerks. All right, guys, let's get started on this part. So in that last section, we found slope, which is rate of change, with 2 points and with graphs, which means since we can do it with 2 points, we should be able to do it with tables, but rate of change is more in relationship with word problems. So again, if it said find the rate of change or find the slope, it would essentially be saying the same thing. But a rate is a comparison between two different quantities. So that just means that we're going to be labeling the rise and the run. So if you drive 288 miles and use 9 gallons of gas, what is your rate of gas consumption? Well, without knowing for sure, because it just says rate of gas consumption, I would assume that this wants to know how many miles you can go on 1 gallon of gas. Okay. Well, here's what it said before. It said you could go 288 miles on 9 gallons of gas. Now, I said I wasn't really sure if it was miles per gallon. There's kind of a way to know, and it kind of has to do with which one would seem more useful. That there is a use for gallons per mile. It's just not as commonly used as miles per gallon, right? Like if you're driving your car, if you figured out how many the miles per gallon, you figured out the gas mileage on this, okay? So I don't know. Gas consumption, gas mileage, I guess it's the same thing. Consumption just, it's kind of a big word. Well, this becomes a proportion that we can solve if we wanted to. But it's a unit rate, by the way, because we're looking at this for every 1 gallon. So really all you'd need to do is go to your calculator, which I'm going to do, and type in 288 divided by 9. And you will have your unit rate, which for me shows as 32 miles per gallon. Let's just use the calculator on that, right? Excuse me. Well, here it comes. It's thinking. There we go. 32 miles per gallon. Now, this one, since it is a rate, in fact, I think even on the homework, you just put in 32, and then it may have something like MPG, right, miles per gallon, or it could be MPH for miles per hour on other problems. But again, I think you'd only have to type in the 32 part of that. Sorry, the reason I point that out, though, is because it is a rate, meaning that you are comparing miles and gallons. I prefer to see these as fractions myself. Again, it just helps me to quantify the miles and the gallons separately. So last week you worked 38 hours and earned $479.94. What was your hourly pay rate? Well, that means that we want to know how many dollars you earned in 1 hour. All right, so that's my rate right there. That's the rate that I want. But what's the rate that I have as of right now? It's $479.94 to 38 hours. Right, and again, this is the nice thing about the unit rate, is all I've got to do is go to my calculator, type in 479.94, and divide it by 38. In my calculator, this even gave us to the nearest penny on that. It's very generous. $12.63 per hour. So again, on the computer, you just probably type in the 12.63 for the homework. So it just may show up as something like this, and then you type in your 12.63 right there, and it may even say like per hour. And yeah, that's another way to know that you're doing it right, is usually when you're doing this on the homework, it'll say, well, just fill in the blank, and then they have it labeled dollars per hour. They don't usually show the 1 right there. It's a phantom 1 per 1 hour. If you prefer to see it that way, that's a 1, not a slash, per 1 hour. All right, for these two, all right, we got this chart that shows living wage jobs in Rochester per 1,000 working age adults over a 5-year period, 97 to 2001. What is the average rate of change, the number of living wage jobs from 97 to 99? And then we'll do 99 to 2001 as well. Okay, so we're not really looking at any of the values between these. I just want to look at 97 to 99 right here. So 97 to 99 like this. And I want to figure out the change in jobs in that amount of time. Well, how much did the jobs change? It went from 620 to 740. Now, if you wanted to do 740 minus 620 to figure that out, you could. Some of you guys are like, I don't really need that. You just know it's a change in 120 jobs, right? Well, how much time changed in between those two? Well, you know that it was from 1999 until 1999, from 1997. And yeah, again, that calculation may have been unnecessary. It's just 120 jobs in 2 years. I'll make this a bit bigger, smaller. There we go. Here's 120 jobs. I'll just put J for jobs in 2 years. There we go. Well, that doesn't tell us the average rate, but it helps us to figure it out. It's 120 in 2 years, so that would be 60 jobs in 1 year. So that's how much they're averaging. Of course, it didn't actually happen that way, which is why statistics like this are slightly manipulative, but that's a whole different ball game right now. So the rate of change on this one, next up, 99 to 2001, right? Different numbers, the process is the same. We got to figure out how much changed from 740 to 810. And again, not everyone needs this, but if you want to use a slope formula, you could, because rate of change is slope. 810 minus 740. Which comes out to 70. So 70 jobs, again, I'll just put a J there for now. And that was in 2 years right there, right? From 1999 to 2001, which is in 2 years. That's an R. Simplifying that, of course, we get 35 jobs per year. And again, I'm showing the 1 right there just because it's a little bit more specific. And again, did it happen to 35 jobs per year? No, it didn't. Which again is why statistics can be very manipulative. All right, here we go. More population problems. But this one's a little bit more specific. We want to find the average rate of change between these two. So did they change exactly this over time? No. Or per year? No. But is it an average? Yes. And averages are very manipulative. So be careful out there, you guys. Well, we got to figure out how much the population changed, and that, of course, would be our numerator on this one. I'm going to start with the later year because, well, it's bigger. Not that it matters. It's end up with the same thing. 2,878,200 people in some city compared to the 2,860,700 people, which was 1947. Now we can go to the calculator and figure this out as well. So I'll clear this for the space, and we'll do 78,200 minus 2,860,700. So that shows a change in the population that was 17,500. So that's how much the population changed. All right. Well, how long did it take? Well, it went from 1947 to 1998. And again, I know some of you guys can do that in your head, but I'm feeling like if I do that in my head, I'm going to make a mistake. So 1998 minus 1947, 51 years. So 17,500 people in 51 years. Let's just divide those now. 17,500 divided by 51. So it does give us a decimal as 343.137. You know, say 1.14. Actually, I'm getting around to the nearest whole person because I don't like to think of people in decimals. It's kind of jacked up, right? So 343 people per year. Now, this is positive. So just a straight interpretation on this one, like 343 people per year, that's okay. We should be able to interpret it from there. But I'm just going to put in there that it's an increase, even though it's already positive. So it's an increase of 343 people per year, whatever city this is, at least for those 51 years. I determined the rate of change from the graph below. What is the slope? This is a redundant question, but I think one is like this on the homework. But if you guys just remember, rate of change is slope. Whatever you find on this is going to be the same. And there's no labels on this one, which is kind of weird that they would ask for a rate of change. No problem. Okay. We can still figure out the rate of change just the same way that we found the slope in the last section on a graph, right? So I got to find any 2 points on this graph that I can actually figure out the coordinates of. So for me, and you may not use the same ones, by the way, you guys. I just kind of see this one right here. And this one. Now, were there others? Yeah, you could have used this one, or even this one right there. Any one of those would work. But the ones that I saw were the red ones, so I'm just going to stick with those, okay? Well, I'm going to make the stair-step thing, right? So we got rise over run, and this one shows it goes down, so I'm just going to write down for now. And then it goes to the right, because for me, it always goes to the right. It goes to the right. Now, before you start just tagging in values on this, right? Because you'd say, oh, it starts here, goes down 1, 2, 3, 4, 5. So it goes down 5. Well, that's true for my y values, okay? It does go down 5. But where we got to be careful is where the scale is different on, in this case, the x-axis. And so you got to check, you guys. Make sure that it's going up or down or left or right by however many the lines represent. So I start right here, and then how far to the right I go? I go 1, 2, 3. But it's not to the right 3, you guys. It's not to the right 3. It's going from negative 60. Oh, was that negative? Yeah, negative 60 to negative 30, it looks like. So it went to the right, but each line in the x-axis represents 10. So since I went to the right 3, each line represents 10, so it'd be actually to the right 30. So our slope is going to be down 5, so that's negative 5 there. And then to the right 30, that's positive 30. And yeah, this can be simplified to be just a negative 1/6. So that's the rate of change, but it's also the slope, because the rate of change is the slope. All right, you guys take a minute and see if you can find the rate of change on this graph, okay? 1 minute, go. So, just like we've done before, just find any 2 points on the line. I'm going to choose 2 that are kind of separated from each other, just so we can see the rise and run. It just makes it writing on my iPad a little bit easier. So I got those 2 points. They're about as far apart as we can get on this graph. So I got my rise over run, right? Well, the rise, this one actually is going to go down. Now again, it's not a matter of counting lines, right? It's going from 4,000 down to 0 right here, which means that we actually went down 4,000 on that one, okay? Now, starting here, that would be where the x is 0, and then we're going to go to the right all the way over to 200. So that's to the right 200 right there, which does make a fraction for us, a ratio of rise to run. Now this 4,000 was down, so just make sure you keep that as a negative, and then it was to the right 200, so that's positive though. Well, this can be simplified by taking negative 4,000 divided by 200. I just cancel out those zeros, which gives us a negative 20 rate of change or slope on this one. Now, just so you guys understand, if we were talking about a 1-to-1 ratio on the axes, the scale for the axes, which is what I would think is most accurate, visually speaking, um, this would be a very, very, very steep line going downward, okay? But because of the way the scale is put onto this graph, it's showing as not so steep, okay? Now, this brings up a point. Well, why would that matter? Well, let's say that this was some kind of statement that you were trying to get people to believe in or maybe purchase your product. Then you'd say, look at this line and how not steep it is, when it really has everything to do with the scales on that, okay? Because the -20 slope, to me, I'd say is a pretty deep slope. So yeah, let's say that you did this the other way, right? Well, uh, yeah, and I'm glad you pointed that out because, like I said before, it doesn't matter which 2 points you guys choose, right? Like if you did choose these two, yeah, you go down 400 to the right 20, bam, it's still the same exact value on that one, right? Is we got well, you'd still have to go to the right, and then you'd have to go down, right? Well, remember, up and down is still the numerator because that's our change in y's, that's our rise. And then left and right is still the denominator, that's the run. So on this one, you're just figuring out the run first, which is still, it's going to be to the right 200, right? Still to the right 200. And then you're still going to have to go down 4,000 to get to that other red point that I'm using. So to the right 200, down 4,000, it still produces the same exact fraction that we had before, which means that it also still simplifies into the -20 right there.